Calculus Video 60, L'Hopital's rule examples and growth rates. So a few more examples here for L'Hopital's rule. Number one here we have the limit as x goes to infinity of the natural log of x divided by x minus 1. So once again, we're going to let x go to infinity, do some direct substitution. We have the natural log of infinity, which is infinity, and infinity minus 1. Which is also infinity. So we get infinity over infinity. That is one of our accepted L'Hopital's rule forms. Remember, for L'Hopital's rule, it either needs to be infinity over infinity or 0 over 0. Then you could use L'Hopital's rule. So the examples I want to show you today all have to do with x going to infinity. That's our focus for the day. All right, so the limit as x goes to infinity, we get infinity over infinity, so we can use L'Hopital's rule, which means we're going to take the derivative of the top, the natural log of x, we're going to take the derivative of the bottom, x minus 1, see what we get. We get the limit as x goes to infinity. Don't forget to write the limit each time. The derivative of natural log of x is 1 over x. The derivative of x minus 1 is just 1. And now if I plug in the infinity as direct substitution, I get 1 over infinity over 1, so just 1 over infinity. And if I have 1 divided by an ever-increasingly larger number, that goes to 0. So our answer here is 0. But I want to talk a little bit more about this problem. So what this is saying is that the rate at which natural log of x is growing is not as fast as the rate at which x minus 1 is growing as x is going to infinity. So although the natural log of x does go to infinity, it doesn't go there very fast, right? The natural log of x looks like this. As x goes to infinity, it does go to infinity, but not very quickly, right? Whereas x minus 1 is this line, x minus 1. As x goes to infinity, this curve gets to infinity quite a bit faster than the natural log of x. It has a larger growth rate. So as x is approaching infinity, the x minus 1 is going to have a much larger y value than natural log of x at every point along the way. So when x is 1,000, 1,000 minus 1 is much bigger than the natural log of 1,000. When x is 1,000,000, 1,000,000 minus 1 is much bigger than the natural log of 1,000,000. The growth rate for x minus 1 is greater than the growth rate for natural log of x. So what we see in our problem here is the x minus 1 has a larger growth rate as x goes to infinity than the natural log of x. Therefore, the x minus 1, if you will, it outweighs the natural log of x. It's larger. And so if we have a smaller thing divided by a much larger thing, that's like 1 divided by the infinity, that answer is going to go to 0. It's going to go to 0 because the x minus 1 grows faster as x goes to infinity. Okay. The goal here is to try to understand a little bit about growth rates of different types of functions. When we do growth rates, though, we're only looking at growth rates as x is going to infinity, not as x is going to 3, right? That's a different story. We can't use growth rates when x is going to 3 or 4 or 0. It has to be when x is going to infinity. Okay, let's try one more of these. What if I have the the limit as x goes to infinity? Again, x is going to infinity here, so we can consider growth rates of e to the x divided by 10x to the third. Okay, first we'll use L'Hopital's rule. We'll figure out our answer, and then we'll kind of go back and think about the growth rates of each of these functions. What is the growth rate of our exponential function e to the x? What is the growth rate of 10 times x to the third as x is going to infinity? All right, so first of all, if I just plug in infinity, I get e to the infinity, that's infinity, divided by 10 times infinity cubed, that's also infinity. And I get infinity over infinity, so I can use L'Hopital's rule. So L'Hopital's rule, we can use it. We get the limit as x goes to infinity. What is the derivative of e to the x? Well, that is just e to the x. Derivative of 10x cubed is 30x squared. Try direct substitution again. Plug in infinities. You get infinity over 30 times infinity squared, still infinity. So let's use L'Hopital's rule again. I'll just go straight over here. Then we get the limit as x goes to infinity. Take the derivative of the top again. That is still e to the x. Derivative of 30x squared is 60x. Again, plug in infinity, and we get e to the infinity is infinity, and 60 times infinity, still infinity. So we can use L'Hopital's rule again. Notice you sometimes have to use L'Hopital's rule multiple times. But I think just one more will work here. The limit as x goes to infinity. The derivative of e to the x, still e to the x. The derivative of 60x, now we're at 60. Okay, now plug in the infinity. And you get e to the infinity, that's infinity, over 60. Okay, this is no longer infinity over infinity. We can no longer use L'Hopital's rule, but that's okay. If you have infinity, right, the numbers ever increasing, divided by 60, the answer here is infinity. So what this is saying is because the limit is going to infinity, the growth rate for e to the x, the growth rate for that, must be larger than the growth rate for 10x cubed. E to the x grows faster as x goes to infinity than 10x cubed does. Therefore, the e to the x is going to overpower the 10x cubed. So even though we're dividing by a number that's getting bigger, the e to the x is getting bigger quite a bit faster. And so we have this, the e to the x overpowering the 10x to the third, and our answer being infinity divided by some number, which ends up going to infinity. Okay. Let's talk about growth rates a little bit more. Growth rates, and we're only considering growth rates. Only consider when x is going to infinity. Not when x is going to 0 or 1 or 4. It doesn't work like that. So only when x is going to infinity. Only when x is getting bigger and bigger and bigger and bigger can we consider growth rates. All right. So here's kind of a list of growth rates we can consider. The natural log of x grows pretty slow. So that's going to be our lower end of growth rates. And I'll use this sort of double less than sign to say the growth rate here is less than, is substantially less than a polynomial growth rate, x to the n. So polynomials grow faster than logarithms. Okay. The next one is that polynomials of a higher degree grow faster than polynomials of a lower degree. So x to the n plus p. In other words, you had x to the n, now we have x to the n plus some numbers. And let's think about n and p here being, or at least p being a positive number. So it's a larger degree polynomial grows faster than a lower degree polynomial. In other words, x cubed grows faster than x squared. X to the sixth grows faster than x to the third. Okay? But all polynomial growth, as x goes to infinity, is less than exponential growth. Exponential growth grows faster, right? An exponential function grows faster than any sort of polynomial function as x goes to infinity. And you might be asking, well, what in the world could grow faster than exponential growth? How about this? How about exponential growth where both the base and the exponent are x? Right, so in exponential, that was like 3 to the x. The base always stayed 3, and the x is increased each time. 3 to the first, 3 squared, 3 to the third, 3 to the fourth, and that grows pretty fast. But x to the x is like, okay, that's like 3 to the third, and then it's like 4 to the fourth, and then it's 5 to the fifth. Not only is the exponent increasing, but the base is also increasing. That's going to grow faster than your traditional exponent. Okay, so those are your growth rates. And so how can we use those growth rates? So for example, let's suppose we were given the problem, the limit as x goes to infinity of x to the fourth over x to the third. Okay, now I could use L'Hopital's rule, I could use our understanding of horizontal and slant asymptotes here, but I could also use growth rates. And what we're saying is x goes to infinity, and it must be x going to infinity, x to the fourth grows faster, x to the fourth grows faster than x to the third. Therefore, the x to the fourth is going to overpower the x to the third, if you will. And since it's growing faster, it's getting to infinity faster, and you get infinity divided by just some number, and you end up with just infinity. Now, you could do L'Hopital's rule here, or you could use growth rates. If you did L'Hopital's rule, right, you'll be taking the derivative 3 times. You have to use the L'Hopital's rule 3 times to get down to where you have just a number in the denominator, and you'll still have an x in the numerator. Now you can give it a shot. Let's take a look at another one though. So there's example 1. Let's look at example 2. The limit as x goes to infinity of 3 times the natural log of x over x. Okay. Thinking about the growth rates, the x grows faster, right? X grows faster. Any sort of polynomial, even raised to the first power, grows faster than the natural log, than a logarithm. So since x grows faster, it's going to overpower the natural log. It's going to have a larger denominator. And if you have a larger denominator, that means this is going to limit it to 0. You're dividing by a larger number than what you have up top. Okay, number 3. How about the limit as x goes to infinity of e to the x over 3x to the 5th? Okay, growth rates say that an exponential like e to the x grows faster than any polynomial as x goes to infinity. Right, it may not always be larger, but as x gets really, really big, e to the x is much larger than 3x to the 5th. Since the e to the x grows faster, the thing that grows faster is in our numerator, so this thing is going to equal infinity. And you could do L'Hopital's rule, you can, or you can consider growth rates. And finally, let's do number 4. The limit as x goes to infinity of x to the x over 5 to the x. Now, if x is 1 or 2 or 3 or 4, the 5 to the x is actually larger. And when x is 5, you have 5 to the x over 5 to the x. Or sorry, 5 to the 5th over 5 to the 5th. But as x continues to get larger, right, 100. 100 to the 100th is larger than 5 to the 100th. So the x to the x grows faster as x goes to infinity. And since it's in the numerator, this thing is going to equal infinity. So that's a little bit more on L'Hopital's rule and growth rates.